Why is it hard to pick theorems for Euclidean geometry proofs? Imagine trying to solve a puzzle where each piece depends on the one before it, but you don't know which piece fits best. That's what choosing the right theorems in Euclidean geometry can feel like. This field is built on a small set of basic rules called axioms, and from these, many theorems follow. The challenge is figuring out which theorem to use for each step in your proof. Since many theorems relying on earlier results, you need to understand which ones are already proven and applicable. If you pick the wrong one, your entire proof might fall apart. Another tricky part is making sure you do not assume what you are trying to prove. In Euclidean geometry, every step must be justified by a previous theorem or axiom. Sometimes, a theorem might seem obvious, but it actually needs a formal proof first. Using it without proof can make your argument invalid. This careful checking makes selecting the right theorem more complex. Geometric figures are often complicated, involving shapes like triangles, circles, and polygons, with many angles and lengths. Recognizing which theorem applies depends on understanding these relationships. For example, knowing when to use the alternate interior angles theorem to prove lines are parallel requires analyzing the figure carefully. If you miss the right conditions, you might choose a theorem that doesn't fit, leading to confusion or errors. Theorems can be proved in different ways, using algebra, synthetic methods, or coordinate geometry. Picking the best approach depends on the problem and what tools you have. Sometimes, a theorem has multiple versions, and choosing the simplest one can save time. But figuring out which version to use adds another layer of decision-making. Foundational ideas like the parallel postulate or the concept of congruence are often subtle. They requiring a good grasp of what they mean to pick the right theorem confidently. For example, the parallel postulate is key to many proofs involving lines and angles, but its subtlety can make it hard to decide how to proceed. Early in Euclidean geometry, some rules like triangle congruence are not assumed but must be proved from the axioms. This means you cannot just use these rules freely. You need to justify them first. That makes choosing theorems more complicated because you need to ensure they are already established. All these factors make selecting the right theorems a careful balancing act. You need to understand the logical structure, verify previous results, and match the theorem to the geometric situation. When you do this well, your proofs become clear and solid. Breaking down complex shapes and relationships into simple, proven steps is what makes learning and applying Euclidean geometry both challenging and rewarding.